Okay, so space physics, unit 6. When we talked about space physics, we divided it into two main sections. The first section, we talked about the Earth and the solar system, and then we expanded our view of the universe. We talked about the galaxies and the whole universe. Okay, first of all, when we talked about the Earth was rotating around its own axis in 24 hours, which is one day. The Earth was tilted at an angle of 23.4 or 23.5 degrees. Okay, and this tilt is what creates the seasons. This tilt is what creates the seasons. If the Earth or the northern hemisphere is tilted towards the sun, we would have summer. If the northern hemisphere was tilted away from the sun, we would have winter. So this tilt is very, very, very important for the seasons on Earth. Okay, and then when we talked about the rising and the setting of the sun, we know that the sun does not rise or set. We call it. It's actually due to what? It's actually due to the rotation of the Earth around its own axis. It's due to the rotation of the Earth around its own axis. So we can see that the sun kind of rises from the east and sets in the west. During the summer, it actually rises from the northeast, okay, northeast and sets in the northwest. So it takes a longer time. It takes a longer time in the sky. Okay, during the summer. That's why we have longer days in the summer and we have shorter days in the winter. So it actually rises from the south east and sets in the south west. That's why we have shorter days in the winter. And then we have 2 days which were called equinoxes on the 20th of March and 23rd of September of each year, meaning that we have equal days, 12 hours of day and 12 hours of night. Okay. And as we can see, the Earth, if it's tilted, this is the northern hemisphere. This is called the northern hemisphere. If it's tilted towards the sun, then this is the summer, as we said. Then the northern hemisphere, if it's tilted away from the sun, then we have the winter. Okay, this is for the northern hemisphere. What about the southern hemisphere? It would be the opposite. If we have summer in the northern hemisphere, then the southern hemisphere would have winter and vice versa. Okay. And then moving on to the motion of the moon, we said that this specific picture was kind of reversed. Why? Because when we start off with a new moon, okay, it moves this way, in which we start off with a waxing crescent, and then not the third quarter, it's actually the first quarter, then a waxing gibbous, a full moon on the 14th of every lunar month. Every lunar month, on the 14th of this month, we would have a full moon. And then moving back, a waning gibbous, and then the third quarter, a waning crescent, and then back to a new moon. A new moon appears when the sun, or actually when the moon is kind of when we have the sun and the moon is behind it. If you have the moon and the sun is kind of facing the moon, it would be a full moon, and that's why it's shining the brightest. Okay, a new moon is kind of a silhouette. It doesn't appear in the sky. Okay, kind of see just a silhouette of this moon. Okay, and then the moon takes around 28 days. Okay, it takes 28 days to complete one full rotation around the Earth. One full rotation. And then when we talked about the orbital speed, any object rotating around another object, if the Earth is rotating around the sun, or if the moon is rotating around the Earth, can we find the average orbital speed? Yes, basically we say the circumference over t, or 2 pi r over t, in which r is the radius of the rotation. R is the average orbital radius. Average orbital radius, and T is the orbital period, the time taken to orbit. So, for example, to find the average speed, average orbital speed of Earth, you might say 2 pi r over t. For example, the distance between Earth and Sun is around 150 million kilometers, or 150, this is 150,000, 150 million, 150 billion meters. While the orbital period is 365 days, but you can convert it into seconds. So you just multiply by 24 hours, 60 minutes, and 60 seconds to find. You can find the average orbital speed of the Earth around the Sun. Again, he could provide you with the radius or orbital radius of the moon, and then ask you to find the average orbital speed of the moon around the Earth. Yeah, it is doable. It is doable. So we have one equation, V equals 2 pi r over t. And then we talked about the solar system, our very own solar system. We had the sun, we had 8 planets, not 9 planets. We have 8 planets, we have dwarf planets. Why? Because Pluto is a dwarf planet, and we have some asteroids and comets. The sun is kind of the center of our solar system. It's the largest object in our solar system, making over 99% of the mass of the whole solar system. The mass of the sun is huge, it's humongous. As we've said before, the mass of the sun is almost 1 million times the mass of our own Earth. That's why it's huge. 1 million times. That's a huge number. That's a huge number. It produces its own light. Okay, that's something we all know because of the nuclear fusion inside the sun. And we will talk later on that the sun fuses hydrogen to produce helium. We can memorize the planets in our solar system by saying my very excellent mother just served us noodles. The first 4 planets are the inner planets. They all have some similar characteristics, which are they are small, similar size, okay, they are rocky and have high density. You can also say that they have high temperatures, relatively high temperatures. Okay, they have high temperatures. Why? Because of the proximity to the sun. While the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, are larger, they consist mainly of gases. That's why the densities are low, and definitely they have low temperatures because they are further away from the sun. And then Pluto, as we said, is a dwarf planet. It's a dwarf planet. It's not a planet. We have asteroids and comets, which are very similar. Asteroids and comets. Asteroids, we might say that asteroids are huge rocks. Okay, just rocks floating in space. While comets are huge rocks as well. But there's a very slight difference between a comet and an asteroid. Why? Because comets have ice. Okay, so as the comets move very quickly throughout the space, the ice can melt when it approaches the sun or whatever. So the ice melts and it forms a tail, as seen in this image. Okay, in this image you have a comet. It has a tail behind it. This tail is created due to the melting ice in space. So it creates a beautiful tail. We can see it for days while viewing it from the Earth. Comets are very rare. We don't see them that much. While view, if we can see it ever, the last comet or the last very famous comet was called Halley's Comet. This was seen back in the 70s, I guess, or in the 80s. Okay, this was a very beautiful sighting. Anyway, how was our solar system created? Due to something called the accretion model of the solar system. The accretion model is a very widely accepted theory of how all of the solar systems throughout the whole universe, not just our solar system, okay, have been created. First of all, you start off with a nebula, with a stellar nebula. It's a huge cloud of dust and whatnot. Okay, this cloud of dust it has nothing. It has just dust, some particles, some molecules, some. Okay, what happens as this cloud of dust starts to rotate around its own self? Why does it start to rotate? Why does it start to rotate? Because at the center, okay, the molecules start to kind of get absorbed towards the center due to the gravity, due to Newton's law when he said any two objects in space will definitely be attracted towards each other. Any two objects in space will be attracted towards each other. So if you have a lot of molecules, we're talking about trillions and quadrillions of molecules that get attracted to each other towards the center of this nebula. As they get attracted, the forces, the force due to the gravity and the temp starts to increase, and the temperature starts to increase, the pressure starts to increase. So you start to kind of create a very small or a baby star. A baby star. We can call it a protostar. Starts to create a protostar. This protostar is it has very extremely high temperatures, and it's still not stable. We will talk later on how can we create a stable star. So in the center of this universe, in the center of this solar system, okay, you have a protostar. This protostar is still getting larger, still absorbing materials, it's still fusing hydrogen. Okay, it's still fusing hydrogen to create helium. And how is this fusion possible? How is this fusion possible? Because it has extremely high temperatures. Why is fusion? It's a valid question. Why is fusion possible in stars but not on Earth? Because in the stars you have extremely high temperatures that we cannot sustain here on Earth. We cannot sustain these extremely high temperatures on Earth. So, due to the fusion, it starts to create heat. It starts to kind of build a protostar, and then you still have a lot of elements. You still have a lot of uh, part of the remaining nebula, which is still rotating around this protostar. Again, these particles start to get attracted to each other, creating small planets. You might call them protoplanets as well. Okay, so you'll start to create protoplanets which are rotating around the sun. Again, with time, they start to take their own shape. Okay, they start to create their own shape, and then they're still rotating in the same direction and in the same plane. They're still rotating in the same direction and in the same plane. The question is, why do the four inner planets have higher temperatures, or not higher temperatures? Why do the four inner planets, why do we call them rocky planets, and why are the outer planets, why do we call them gaseous planets? It's because of the temperature of the sun. It's because of the temperature of the sun during the formation of this solar system. While forming a protostar and protoplanets, the temperatures were extremely high. So the gases in the four inner planets couldn't sustain these very high temperatures. So they kind of escaped. They kind of escaped outwards. They kind of escaped outwards towards the outer planets. They wanted to escape the high temperatures. That's why what remained was what were the more dense materials, such as rocks, such as metals, and whatnot. So the four inner planets sustained these high temperatures but kind of lost most of the gases. Most of the gases were lost by the inner planets. The outer planets attracted these gases and formed gaseous planets, and that's why their densities are much lower than the densities of the inner planets. They have a huge volume, yes, huge volume, but the density, if you calculate the average density of the whole planet, it would be much less than the density of the inner planets. Okay, our solar system formed around 4.5 billion years ago, and then we keep on talking about the whole accretion model. Okay, again, the sun, okay, fuses hydrogen to form helium. It fuses hydrogen to form helium. Okay, when we talk about distances in space, if we talk about distances in space, I stated that the distance between the Earth and the Sun is around 150 billion meters, or 150 million kilometers. 150 million kilometers. which is not a huge distance. Okay, this number is actually not 510 to the power of 12. It's 5 times 10 to the power of 12. 5 times 10 to the power of 12. So this is kind of the radius, if you might say, the radius of our solar system. 5 times 10 to the power of 12 meters from the sun. Okay, the speed of light. What is the speed of light? We know that the speed of light is 3 times 10 to the power of 8 meters per second. 300 million meters per second. 300 million meters per second. Right? And we just said that the distance from the Earth to the Sun is 150 billion meters. 300 million 300 million is much smaller than 150 billion. 150 billion, that's a huge number. That is a huge number. So that's why it takes almost 8 minutes. It takes the light almost 8 minutes to travel from the sun to the earth. 8 minutes. 500 seconds, almost 500 seconds for the light to travel from the sun to the earth. And that's a small distance when comparing the distances in space. When we say 8 minutes, the light takes 8 minutes to travel from the sun to the earth. Well, that's actually a very short distance. 150 billion kilometers, 150 billion meters, that's a very, very short distance. Why? Because if we leave our star and decide to find another star, okay, we got fed up from our sun and we need to find another star. The closest star, it's called Proxima Centauri, I guess. The light takes 4 years to travel from that star to our own Earth. Light takes 4 years to travel from that star to our own Earth. Again, our star sends light in 8 minutes. That other star, Proxima Centauri, sends light in how many years? In how many years? Not minutes, not hours, not days, not months. 4 years. It takes light 4 years to travel. That means that the light keeps on traveling in space for a distance of 4 light years. For a distance of 4 light years. So we will come up with a new unit of distance, which is called a light year. I will discuss it later on. I will discuss it later on. A new distance in space, which is called a light year, which is the distance traveled by the light in 1 year. We can find this distance by saying speed equals distance over time, and time equals distance over speed, or distance equals speed times time. And we will solve it later on. Okay, light traveling in space. Okay, elliptical orbits. Elliptical orbits. Any planet. It rotates around the sun in an elliptical orbit, not a circular orbit. Not a circular orbit. You might say, so that means that the distance between the Earth and the Sun isn't exactly 150 billion meters, which is correct. We say that this is the average distance. It's the average distance. We might find the longer distance and the shorter distance, okay, and we can say that this is the average distance between the Sun and the Earth. And not to be mistaken, please do not be mistaken. If the Earth is at this position, or at this position. If we say at position 1 and position 2, you might say, okay, so at position 1, the Earth, this is summer for Earth, and at position 2, this is winter for Earth, because at 1, it's closer to the sun, and at 2, it's further away from the sun, which is wrong. Which is wrong. Again, we said that the seasons depend on what? They don't depend on the proximity to the sun. No, they depend on whether the hemisphere is tilted towards the sun or away from the sun, whether it's tilted towards the sun or away from the sun. And in fact, actually, Earth, okay, Earth, when it's at the furthest distance from the sun, it's actually tilted towards the sun. So the northern hemisphere is tilted towards the sun. So actually, at position 2, this is I'm talking about true facts. On Earth, when it's at position 2, it's when it's at the furthest distance from the sun. This is when summer occurs on the northern hemisphere, and then when it's at the position 1, it's actually facing the other way, which is winter. So it does not depend on the distance between Earth and the sun. No, it depends on whether the hemisphere is tilting towards the sun or away from the sun. Okay, let's get back to our elliptical orbits. Okay, Elliptical orbits, again, the Earth rotates around the Sun in elliptical orbit. Um, and this kind of has to do with the law of conservation of energy. What do I mean by the law of conservation of energy? Energy cannot be created nor destroyed as the Earth rotates. The types of energy stored inside the Earth differs. Types of energy differ. How do they differ? When the Earth is very close to the sun, when the Earth is very close to the sun, it gains kinetic energy. So the kinetic energy increases as it's very close to the sun. As it moves away from the sun, the kinetic energy decreases. Kinetic energy decreases. What happens to this energy? It's not lost. Energy is not lost. It's actually converted to gravitational potential energy. So at the furthest point from the sun, the Earth has the greatest gravitational potential energy and the least kinetic energy, while at the closest point from the sun, it has the greatest kinetic energy and the least gravitational potential energy. And it keeps on rotating in this orbit, gaining and losing, increasing and decreasing the kinetic and gravitational potential energy. This is an elliptical orbit. Okay? And then if we talk quickly about the planets, we can just kind of memorize. You don't need to memorize. You don't need to memorize this table. But if you think about the table, okay, you have the sun, for example. The mass of the sun is 2 times 10 to the power of 30, while Earth is 6 times 10 to the power of 24. That's why we say that the sun is 1 million times larger than the Earth. Okay, and if we compare the densities of the inner planets to the outer planets, and Mars is included, okay, these are the inner planets. If you compare these densities to the outer planets, you will find that the outer planets are less dense, much less dense. If you think about the radius of Jupiter, for example, is 7 times 10 to the power of 8. 7 times 10 to the power of 8, while Earth is only 6.4 times 10 to the power of 6. Venus times power 6, Mercury power 6, okay, Mars power 6. So they're all close in their size. They're all kind of close. Saturn is something to the power of 7, power 7, power 7. So that's why we call them gaseous giants. Gaseous giants. Okay? Okay. And then moving on to stars and the universe. Want to expand our vision a little. Our sun, our very modest sun, is a medium-sized star, okay, consisting mainly of hydrogen and helium. These hydrogen and helium, okay, we know that hydrogen fuses and produces helium. Um, the three main energy or the three main electromagnetic waves produced by the sun are infrared waves, light waves, and ultraviolet rays. The three main electromagnetic waves produced by the sun are these three waves. Okay, if a sun or if a star uh, is white or blue, they are hotter and brighter than those are that are red and yellow. So red and yellow are kind of colder than white and blue stars. Okay. Okay. Again, why is hydrogen fusion not currently possible on Earth? Because the main problem is that hydrogen nuclei require very high temperatures. Okay, require very high temperatures. There's an S missing here. Okay, to fuse together. Okay. And then moving on to our galaxies. Our own galaxy, the galaxy that we live in, is called the Milky Way. It's called the Milky Way. And the Milky Way is 100,000 light years. What do I mean by 100,000 okay, light years? Meaning that if you have a laser at this end of the light year of this end of the Milky Way, and you switch on the laser, this laser would take 100,000 light years to travel all the way to the other side of the Milky Way. 100,000 light years. It takes 100,000 years to travel this whole distance. 100,000 years traveling this whole distance. It's a huge number. Extremely huge number. Our Milky Way consists of what? It consists of billions, hundreds of billions of stars, hundreds of billions of stars in our own Milky Way. So one galaxy, the Milky Way, has up to 400 billion stars. has up to 400 billion stars. The next question is, how many galaxies are there in the universe? If this is our own Milky Way, which is one galaxy, are there hundreds of galaxies? Are there thousands of galaxies? Millions of galaxies? How many galaxies are there? Actually, there's an estimate that there are 100 billion galaxies. 100 billion galaxies. And to be honest, the newer update, okay, it's not included in this in your syllabus, okay, but the most recent studies state that there are around 2 trillion galaxies. Most recent studies say that there are at least, no, they're saying at least 2 trillion galaxies, if not way much more. If not way much more. So, if we say only 100 billion galaxies, if we assume that there are only 100 billion galaxies, each galaxy contains at least, let's say, 200 billion stars with an unknown number of planets. So you can just start to think about the number of stars that there are in this whole universe. This universe is huge. Okay, it's not just huge; it's way more than way much bigger than you can ever think of. Okay, you cannot think about the whole how huge this universe is actually. Okay, distances, as we said, are huge in the galaxies, okay, between galaxies, between the whole universe. Okay, if we say 1 light year, what is 1 light year? Let's say it's the distance traveled by light in 1 year. How can I calculate 1 light year? Okay, as we said, that the distance is equal to the speed times time. So you can say that the speed of light is 3 times 10 to the power of 8 times the time in 1 year. The time in 1 year, which is 365 times 24, okay, times 60 times 60. So this is the speed times the time, which gives you 2.5 times 10 to the power of 15 meters. 9.5 trillion kilometers, or you might say around 10 million kilometers. 10 trillion kilometers. That's a huge number. 10 million kilometers. Okay, 10 trillion kilometers. That's just 1 light year. That's just 1 light year. We said that the closest star is 4 light years away, meaning that it's 40 trillion kilometers away. What about the whole our own Milky Way? It's 100,000 light years. So you can just multiply 100,000 times 10 trillion and figure out that huge number. We're just talking about this light year. Let me give you another fact, okay? The radius or the diameter, okay, the estimated diameter of this universe, is around 150 billion light years. 150 billion light years. That's يعني not just huge, that's huge. It is huge. Yeah. So 150 billion light years, that's the diameter of our universe. It's too large. Too large. Anyway, not waste too much time thinking about the vast massiveness of this universe. If we talk about the life cycle of a star, any star starts off with a nebula. Which is a giant interstellar cloud of hydrogen gas and dust, which we call a nebula. Okay, all of the stars around us in the universe start off as a nebula. And then the force of gravity within the nebula. Remember when we talked about the accretion model, okay? So the force of the gravity in this nebula starts to pull them together until it forms a protostar. What is a protostar? It's a baby star. Okay, as the particles are pulled together, the density increases, and thus resulting in more frequent collisions between the particles, causing the temperature to increase. So the temperature keeps on increasing while creating a protostar. So we have two forces now. Now we have two forces. What are these two forces? You need to think about them. What are these two forces? You have the inner force due to the gravity. Okay, you have the pulled closer together due to the gravity, and then you have the outer forces due to what? Due to these nuclear fusion. Due to the nuclear fusion. So we have two forces which we need to keep on thinking about while talking about any star, whether it was a protostar, a main star, okay, what star is dying. What is a main sequence star? It's a stable star. Our sun is a stable star now. Our sun is a stable star now. Okay. Once the protostar becomes hot enough, nuclear fusion reactions, okay, begin within the core. Once a protostar is formed, it will depend on its mass. It will depend on its mass. If it is an average star or if it's a massive star. Our sun is an average star. A massive star is a star that is at least, some people say at least 8 times, some people say at least 10, 20, whatever, but any massive star must be much, much larger than our own sun. Okay? Must be much larger than our own sun. Our sun is an average star. Okay, okay. So now we have two types of stars. Either it's an average star or a massive star. They are both now a main sequence star. What do we mean by main sequence stars? Meaning that the forces are equal. What are the forces that are equal? The inward force due to gravity is equal to the outward force or outward pressure due to the fusion reactions. You have two forces which are equal. It's kind of in equilibrium, you might say. Okay, so the star isn't shrinking, it's not expanding yet. Okay, it's stable. We call it a stable main sequence star. Okay, then after a couple of billion years, billions and billions of years, okay, the amount of hydrogen, we have a finite amount of hydrogen atoms in any star, right? There are trillions, quadrillions, quintillions, septillions. Okay, we have huge amounts of atoms, of hydrogen atoms that keep on fusing for billions and billions and billions of years, right? But at the end of the day, it's a finite amount of elements, a finite amount of hydrogen elements, hydrogen atoms. When these atoms start to run out, when these atoms start to run out, what happens to the star? After billions of years, okay, they will start to run out. This causes the core to shrink up, to shrink and heat up. When the core shrinks, the inward force due to gravity becomes greater than the outward force due to the pressure. So first, okay, the inward force due to the gravity becomes greater than the outward force due to the pressure. Why? Because the amount of reactions decreases. The amount of reactions, the amount of nuclear fusion reactions that push outwards start to decrease. A new series of reactions starts to form. For example, helium starts to fuse together. Helium starts to fuse together. When helium fuses together, they start to create beryllium. Okay, helium atoms start to fuse together, creating what? Creating beryllium atoms, which is unnatural. Which is unnatural for any star. A star, a natural star, a stable star, it fuses what? It fuses hydrogen to create helium. So when you fuse helium to create beryllium, this is an unnatural thing for the star. And this fusion actually gives off much greater outer forces, much greater outer forces, and therefore the star starts to expand. The star starts to expand. And then, as it expands, it becomes either a red giant or a super red giant. A red giant or a super red giant. A red giant is formed if you have a medium sized star like our sun. A super red giant is if you have a massive star, a star which is much larger than our own sun. So both stars will go through the same process. You'd either have a red giant or a supermassive red giant. Okay, a red super giant. Okay, let's talk about red giants, our small stars, our medium-sized stars, as they create red giants. Once the red giant start to expand, the helium starts to run out, the beryllium starts to run out, and once the star starts to form iron, once the star starts to form iron, you keep on fusing elements, you fuse elements, and then you fuse beryllium to create larger elements, and then larger elements until you reach a very specific dangerous element, an extremely dangerous element, which is the iron. What happens when the star creates or fuses iron? When the star fuses iron, okay, creates iron, iron is a very good conductor of heat. So kind of absorbs a lot of the heat. It kind of absorbs a lot of the heat, and therefore, once it creates iron, it's seconds away from blowing up. It is seconds away. A star could be a red giant, could remain as a red giant for hundreds of millions of years. It could remain as a red giant for a very, very long time. But once it creates, it keeps on expanding, expanding, expanding. And once it creates iron in the core, it blows up. If a red giant blows up, it will create a planetary nebula. It will create a planetary nebula, which again is it ejects dust and gas. Okay, again, kind of a nebula. Gas is everywhere. It's a huge explosion in space. Okay, which is called a planetary nebula. Red giant gives off a produces a planetary nebula and a white dwarf. A white dwarf is a very, very small star, a very small star, okay, which is kind of the core of the old star, of the mother star. It's the core of the mother star. Okay, this is what is left behind. So when it blows up, when a red giant when a red giant blows up, it gives what produces a planetary nebula and a white dwarf. White dwarf will cool down eventually, okay, emitting most of the energy, and therefore after maybe a couple of billion years again, the black dwarf, okay, forms because also the sun is kind of dead. The sun is kind of dead. Why? Because all of the energy is emitted or radiated to the space, and it will disappear because it's pitch black. You cannot see it. What about if we had a super red giant? So this red giant has a very small, a very short process. It creates a planetary nebula, a white dwarf, and then a black dwarf. What about a super red giant? A super red giant. It has much, 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 much more mass. Okay, the sun is much more massive. Okay, a super red giant creates a supernova. Super, they are all super together, so creates a gigantic explosion called a supernova. This supernova again gives creates a planetary nebula or whatever, but the core remaining is called a neutron star. It's called a neutron star. What is this neutron star? It's a very, very intriguing thing. What is a neutron star? Basically, this neutron star is created when the forces or when the pressure is too high, when the pressure, okay, of the explosion is too high. And therefore, okay, listen up, therefore, the electrons are pushed inwards. The electrons, they're not in the shell anymore, they are pushed inwards. And they kind of fuse together with the protons, creating neutrons, which is, if you think about it, this is the reverse operation of producing a beta particle. Okay, if you remember Unit 5 atomic physics, okay, how do we create a beta particle? We split a neutron into a proton and an electron. But in a neutron star, this is the reverse process in which you fuse an electron with a proton, creating a new neutron. What happens to the shell? Okay, the shell is kind of it's destroyed. There is no shell anymore. There is no shell for this atom anymore. So all of the atom is compressed into the size of the nucleus. All of the atom is compressed into the size of the nucleus. And if you think about it, okay, if we had, okay, let's give a simple analogy. If we have atom, one atom, which is the size of a huge football stadium. One atom, which is the size of a huge football stadium. Okay, this is the atom. The nucleus of this atom would be a very small football in the center of this stadium. So if you think about it, when you compress this whole atom into the size of a football, you can imagine the density of this atom. The density of this atom. So neutron stars are extremely dense. Okay, they have densities which are, I don't remember how much. I think it was something times 10 to the power of 8 or something times 10 to the power of 9 kilograms per meter cubed. Okay, billions of kilograms per meter cubed. Okay, so this is a neutron star. It's a neutron star. And then it could either create a neutron star or a black hole. It could either create a neutron star or a black hole. If the sun or if that star was much bigger, we have a massive star, it will create a neutron star. What if it's a super, super, super massive star? It would create a black hole. A black hole is simply a very small, okay, point in space, okay, which absorbs literally or attracts literally everything around it. It attracts why does it attract everything around it? Because of the density. It's super dense. It's super dense. Again, if you think about Newton, when he said anything, any two objects in space will be attracted towards each other. Any two objects in space will be attracted towards each other. So if this mass, okay, is super dense, it will attract literally anything, even light. Even light cannot escape this black hole. What happens to a black hole? We do not know yet exactly what happens inside the core of a black hole. But I know some of you might think this is a portal into a different universe or into a different timeline or whatever. No, it's not. It's not actually a portal. What you're thinking about isn't a black hole. It's called a wormhole, which is a totally different theory. It's an unproven theory. Wormholes are unproven theories. If you go into a wormhole and then just suddenly come up on the other side of the universe or in some other dimension or in some other timeline, you might be thinking about wormholes, which are unproven. Unproven. They're just theories. But black holes are proven. We have found black holes. We know that the center of our universe, our own galaxy, our Milky Way, has a supermassive black hole in the center of this galaxy. All of the stars and all of the planets in the Milky Way are rotating around this galaxy, around this supermassive black hole, and eventually we will all be absorbed by this supermassive black hole. Maybe after a couple of trillion years, maybe if someone could live up to that time, maybe he would see us while being absorbed into this black hole. Okay, now the expansion of the universe. The expansion of the universe. We've all said before, the universe is expanding, the universe is expanding. How do scientists, or how can scientists prove that the universe is expanding? Scientists have been looking at galaxies, okay? So we view galaxies that are very, very distant, extremely distant galaxies, not close galaxies. For example, our closest galaxy is called Andromeda, which is a couple of million light years away, which is relatively close, relatively close. We actually look at very, very distant galaxies, hundreds of, tens of billions of light years away from us. When we view these galaxies, when we look at these supernova created by these galaxies, supernova, if you remember, is the death of a supermassive star. You might say, how do they know that this star will blow up, or how do they know that this supernova will occur at this time, or whatever? They don't actually know, but due to the immense amount of stars in every galaxy, I said that every galaxy has billions of stars, so it's very probable that you would, if you view if you look at a galaxy long enough, you would see a supernova. So, what do scientists do? They look at the supernova of the very distant galaxies, supernova of these very distant galaxies, and they kind of look at the brightness of these supernova. They view the brightness of these supernova. The colors or the light emitted from these supernova are slightly different than the colors emitted by or any colors here on Earth. What do I mean by slightly different? Okay, these colors are red shifted. They are red shifted, which is a very, very important notion. We need to understand it thoroughly. What is red shift? Red shift is when actually, the redshift depends on something called the Doppler effect. Let me explain first of all the Doppler effect. What is the Doppler effect? If you have, for example, an ambulance, okay, which is moving towards you, it has a siren, okay, this ambulance is moving towards you. It has a siren, the siren is on, so as you hear the siren, as the ambulance is moving towards you, the siren kind of has an increased frequency. The frequency increases as the siren, as the ambulance is moving towards you. When the frequency of a wave increases, the wavelength of this wave decreases. Okay, speed equals frequency times wavelength. So as the ambulance is moving towards you, the frequency increases. It becomes much more high pitched. It hurts you much more. So as the ambulance is moving towards you, which is intentional. Anyway, this is Doppler's effect. Okay, so when the ambulance is moving towards you, the frequency increases and therefore the wavelength decreases. Once the ambulance passes by, as it's moving away, as it's receding, we might say, as the ambulance is receding, it's moving away. What happens to the frequency? Frequency actually decreases. The frequency decreases. So when the frequency decreases, what happens to the wavelength? The wavelength increases. And this is what we care about. This is what we care about when the wavelength increases. Let's talk about the colors. Let's talk about the colors. What are the colors that we know of? What is the spectrum of colors that we know of? Roy Gibiv. We know Roy Gibiv. So as the wavelength increases, which of these has the longest wavelength? Red. Which of these has the longest wavelength? It is the red. So as the wavelength increases, we move towards the red. And that's why we call it a red shift. That's why we call this phenomenon a red shift. Again, I do not understand. How does it get red shifted? These galaxies are moving away. These very distant galaxies are moving away, and they aren't moving away very slowly. Actually, they are moving away very extremely fast. Okay, with speeds that are very close to the speed of light. The most distant galaxies are moving away with speeds very close to the speed of light. Okay, actually, some scientists say that the universe is expanding with a speed much faster than the speed of light. The universe is expanding with a speed much faster than the speed of light. Anyway, back to our point. These very distant galaxies are moving away, and therefore the frequency is decreasing, the wavelength is increasing. So when you view the supernova of these galaxies, what happens to the light produced by these supernova? The light has a redshift. The light is red shifted, meaning that the wavelength increases. Therefore, this is proof. This is proof that the universe is expanding. The universe isn't constant. The universe doesn't have a set diameter or whatever. The universe is expanding day after day after day. So when the universe keeps on expanding, after 1,000,000 years, it will have grown much larger. What happens if I go back in time? What happens if you go back in time? So today the universe, let's say, is 150 billion light years across. If I go back in time, would this number decrease? Yes, it would decrease. I will go back a couple of years. I will go back hundreds of years, thousands, millions. How long ago can I go back in time? Until the size of this universe becomes almost zero. How long ago can I go back in time until this size of the universe becomes almost zero? The scientists kept on studying this, and they found out that the universe is almost 14 billion years. So you can go back in time 14 billion years until the whole universe has shrunk into this very small point of energy. This very small point of energy is what created this whole universe. This whole universe, okay, was created due to this very small point of energy in a process called the Big Bang. Okay, in a process called the Big Bang. Okay, all of the universe, all of the mass, all of the energy, everything we know of was created at that instant. When this point blew up, energy started to scatter all directions. There were no directions. Actually, there is no distance. There is no time. Time and distance were created at that instant. That instant. And due to Einstein's equation, when he said E equals mc squared, we can say that energy did create the mass, and vice versa. So yes, energy did create the mass. Okay, the energy did create the mass in this Big Bang.
The Big Bang created all of the masses of all of the stars and all of the galaxies we know of. Due to what? Due to this Big Bang theory. Again, some scientists have also viewed something or have detected detected some radiation throughout the space. Okay, some radiation throughout the space, which was called the microwave background radiation, sometimes called the CMBR, cosmic microwave background radiation. This cosmic microwave background radiation, they found out that it was equal throughout the whole universe. If you look at any part of the universe and try to measure the amount of CMBR, it would be equal throughout the whole universe. Meaning that this whole universe was created from a one point, was created from one point. This radiation fills the whole universe with an intensity that is equal in all directions. Okay, when was this cosmic microwave background radiation created? When the Big Bang happened, 14 billion years ago. 14 billion years ago. How did they come up with this number? How did they come up with this number? Hubble's constant or Hubble's law states that V equals h naught times d. V equals V is speed, okay, we know V is speed or velocity, D is distance, okay. What is h naught? What is h naught? H naught is Hubble's constant, okay, Hubble's constant. He found out that when he viewed these very distant galaxies, now we're looking at distant galaxies, and we are finding the distance because of the redshift. Okay, we can measure the distance, we can measure the velocity of these very distant galaxies. We can measure these distances. He found out a very weird phenomenon, which was that if you had much more distant galaxies, then these galaxies had much higher speeds. If you had closer galaxies, then they had much lower speeds. And it was equal. This ratio was equal throughout all of the galaxies that he viewed. This ratio was equal throughout the whole, literally every galaxy he viewed, okay, had this exact ratio, which he came up with h naught, which was Hubble's constant. This constant was around 2.2 times 10 to the power of negative 18 per second. 2.2 times 10 to the power of negative 18 per second, which was Hubble's constant. Okay, this is Hubble's constant. Okay, so how can we use it? We have the equation V equals h naught times distance. For example, a galaxy 1 million light years away is receding at a speed of. Can I find the speed? Can I find the speed of a galaxy that is 1 million light years away? Yes. H naught times distance. So H naught is 2.2 times 10 to the power of negative 18. The distance is 1 million light years. So 1 million times the distance of a light year, which is 2.5 times 10 to the power of 15 meters. Again, you need to use SI units. You need to use SI units. So this would give you a speed of 20,000 meters per second, around 21,000 meters per second, or 21 kilometers per second. Again, please do not get mixed up. You need to use, okay, you need to use SI units. If you have kilometers, if you have days, if you have hours, light years, whatever, convert everything to seconds and meters. Convert everything to seconds and meters so that you do not get mixed up while solving these very not complicated equations. They're not complicated. They're just complicated because you have huge numbers. You have huge numbers. That's what makes them a bit complicated. Okay, and then he came up with the age of the universe by saying, well, what happens if we say 1 over h naught? Because of most distant galaxies, the most distant galaxies, 1 over h naught was what? Was 4.5 times 10 to the power of 17 seconds. This is 4.5 times 10 to the power of 17 what? Seconds. Can I find the age of the universe? Yes, if you have them in seconds, can I find it in years? Yes, just divide by 365, 24, 60, and 60, giving you a time of around 14 times 10 to the power of 9, or 14 billion years. 14 billion years. And this is the time or the age of the universe. Okay? Well, that's it for explaining Unit 6. That's it for explaining Unit 6. Can we solve a couple of questions regarding Unit 6? Yes, we can. Okay, let's solve a couple of questions, and that will be it for today. Okay, so if I open up Unit 6 in Paper 4, okay, let's open up Paper 6 together in Unit 4. Unit 6, Space Physics. Can you all see Space Physics now? Yes? Okay, let's solve a couple of questions, and that will be it for today. Are you all ready? I hope you are. Huh. Let's go. Let's go. Question 1. Time taken for Mars to orbit the Sun. Okay. Time taken um, for Mars to orbit the Sun is 690 Earth days. The average orbital radius of Mars. Okay. Can you all see the screen? Can you all see the screen, Shabab? I think you can see the screen now. Yes. Okay. So the average orbital speed, he wants to find the average orbital speed. Okay, if the orbital time, this is the orbital time, orbital period. Okay, orbital period. The average orbital radius is 2.2 times 10 to the power of 10 kilometers. Can I find the speed in kilometers per second? In kilometers per second. So the average orbital speed was what? Average orbital speed was v equals 2 pi r over t. He wants the speed to be in kilometers per second. Okay, 2.2 pi times the radius, which was 2.28 times 10 to the power of 8 kilometers. So I'll leave it as this. Kilometers, because he wants kilometers per second. I will leave it as it is. Over the period, which was 690 days, 690 days times 24 hours times 60 minutes times 60 seconds, because you want it in seconds. Okay, so you want this in kilometers and you want this in seconds. So this would be okay. If you calculate it using your calculator, it would give you an average, okay, around 24 kilometers per second. 24 kilometers per second. State the shape of the orbits of the planets. The orbits of the planets are elliptical. Or elliptical. Light from a distant galaxy is redshifted. Explain what is meant by redshift. What is meant by redshift? The wavelength. What happens to wavelength? Does it increase or decrease? Wavelength increases when? When does the wavelength increase? When does the wavelength increase? Wavelength increases. Wavelength increases when the galaxy is moving away. When the galaxy is moving away. Okay, state the quantity that the redshift of the galaxy is used to calculate. Okay, the quantity that is used to calculate is the speed of the galaxy. We can see, okay, we can find the distance, but we use it to find what? We use it to find the speed, okay, of the moving galaxy. The speed of the galaxy. Pluto is a dwarf planet. Figure 10.1 shows the direction and motion of Pluto. Okay, point X is the point closest to the Sun. Y is the furthest away from the Sun. The orbital speed of Pluto varies as it orbits the Sun. Describe how the speed of Pluto varies as it moves away, as it moves from X to Y and then back to X. From X to Y and then back to X. So from X to Y. What happens to speed? What happens to speed? Speed decreases. Speed decreases. And then from Y to X, what happens to speed? The speed again increases. Speed increases due to the law of conservation of energy. Then explain in terms of energy transfers why the speed of Pluto varies in this way in terms of energy. In terms of energy, which point has the highest kinetic energy? Which point has the lowest kinetic energy? The lowest kinetic energy is at Y. Lowest kinetic energy is at Y. So at Y, you have to say, we need to say at Y, It has the lowest kinetic energy and highest gravitational potential energy. Okay, as it moves, as it moves to x, the gravitational potential energy decreases and kinetic energy increases. Okay, and then you can say at x it has the highest kinetic energy. At x it has the highest kinetic energy and the lowest gravitational potential energy. Okay. B. The temperature of Pluto is 43 degrees Kelvin. Can I convert it to Celsius? Yes. We know that Kelvin. How can I find it in Celsius? We know that Celsius is equal to Kelvin plus 273. So basically 43 plus 273, which would give you negative 200. I'm sorry, it's not plus, it is minus. Okay, it is minus. Why? Because the temperature in Kelvin, okay, temperature in Kelvin is 43. So you minus 273, which would give you negative 230 degrees Celsius. Negative 230 degrees Celsius. Okay. Kelvin is actually equal to Celsius plus 273. At 0 degrees Celsius, the temperature in Kelvin is, at 0 degrees Celsius, the temperature in Kelvin is 273. Okay. Pluto has a white surface. As shown, Pluto rotates. The white surface alternately faces towards and away from the sun. Explain how this affects the temperature of Pluto as it rotates on its own axis. When it has a white surface, when Pluto has a white surface, what happens? White surfaces, are they good or poor absorbers of infrared radiation? We know that they are poor absorbers of infrared radiation. So the temperature will increase when it's facing the sun. When it is facing the sun, the temperature will increase. And when it's facing away from the sun, the temperature will decrease. But because of this white surface, because of this part, which is the white surface, you can say as it's facing the sun, as it faces the sun, okay, the temperature increase, the temperature increase is less, okay, and as it faces, okay, away from the sun, okay, the temperature decrease is also less. The temperature decrease is also less. Okay. Okay, let's solve one more question and that would be it for today. State the equation that defines the average orbital speed. State the meaning of any symbols you use. So V equals 2 pi r over t, in which r is the orbital radius, radius, and t is the orbital period, the time taken to rotate around whatever it's rotating around. Suggest why countries that are significant distance from the equator experience significant temperature variations throughout the year. Significant temperature variations around. Why? Because of the tilt of the Earth. Okay, because of the tilt of the Earth. Throughout the year, the Earth alternately faces the sun and then away from the sun. Keeps on facing the sun and away from the sun. So the angles of these rays that are coming from the sun, the angles of the rays that are coming from the sun differ throughout the year. Okay, the angles of the rays that hit or that reach these, the angles of the rays that hit these parts differ throughout the year. Okay, so the rays that angles of the rays coming from the sun differ throughout the year. Throughout the year. There's a question, someone saying, why is the temperature increase when it's facing away from the sun? When it's facing away from the sun, it gets colder. Okay, for the previous question, when it's facing away from the sun, it gets colder, and that's why the temperature decreases. But we're going to say that the temperature decreases at a much less rate because it has a white surface, because that part is a white surface. Fill in the gaps. For a star that is much more massive than the sun, much more massive than the sun. The stage that follows the stable star is the after the stable star. It becomes what? After the stable star, if this is a massive star, this is a massive star, it becomes a super red giant or a red super giant. Okay, a red super giant because it's a much more massive star. It then explodes as a supernova to form something. Supernova forms what? Supernova, any explosion, literally any explosion, whether it was a supermassive star or just an average star, it will definitely form a nebula. It forms a nebula. And then this leaves behind, if it was a supermassive star, it will leave behind something, okay? Either a neutron star or a black hole. Okay? Either a black hole or a neutron star. A galaxy is moving away from the Earth with a speed of 33,000 kilometers per second. The value of Hubble's constant is 2.2. Calculate the distance from the Earth. Can I find the distance? Okay, so we know that the equation V equals h naught times distance. To find the distance, we would say velocity over h naught. We want the distance in light years. Okay, I will find the distance and then I will convert it into light years. I will just find the distance. Now we have the speed is in kilometers per second and the Hubble's constant is per second. So to find the distance, the actual distance, it would be 33,000 kilometers per second. I will multiply it by 1000 to find it in meters per second, divided by h naught, which was 2.2, okay, times 10 to the negative 18, okay. Let's use our calculator to find this first number. 33,000 times 1000 divided by 2.2 times 10 to the negative 18. This is a humongous number, which is 1.5 times 10 to the power of 25 meters. 1.5 times 10 to the power of 5 what? Meters. If you can recall, one light year was what? One, if you can recall, one light year was 9.5 times 10 to the power of 15 meters, right? 9.5 trillion kilometers. So 9.5 times 10 to the power of 15 meters. Can we just divide it? Yes, we can divide it. So we can divide this number by 9.5 times 10 to the power of 15. Okay, again, please use parentheses while solving these questions. Use brackets or parentheses while solving these questions. Okay, so if you divide it by 9.5 times 10 to the power of 15, this will give you a large number, which is 1.5 times 10 to the power of 1.57 times 10 to the power of 9. Okay, 1.57 times 10 to the power of 9 light years. This is the distance of this very distant galaxy. Okay? Okay. And that's it for our revision sessions.